Okay. Screen sharing check. iPad on check. Apple Pencil check. Everything is check. Camera on check. Jawline popping check. All right. Okay. So all that being said and done, well, it's been a crazy week. I'm not gonna lie. I'm pretty sure it has been the same for you. This week was a week for me, just inside basement. Like I'm talking 8 a.m. till 5 p.m. and plus, just inside basement, just locked in grinding, trying to get everything done. And sometimes it just turns into a solo grind, but it is what it is. You gotta do what you need to do in order to get an A plus, And you know me, I'm always gonna shoot for the best. A usually always shoots for the best, and I'm pretty sure anyone in the side basement has pretty much the same mentality. So what are we gonna talk about today? So in the last video, we talked about Miller's theorem and capacitances, how you can split capacitances and then find the poles from there. Today, we're going to expand further on that topic, and we're going to talk about the intrinsic capacitance of BJTs and MOSFET. I'm going to focus on a MOSFET example. The theory is pretty much the same for the BJTs as well. So if you understand a MOSFET, which in my opinion is more complicated because a MOSFET does have four intrinsic capacitors and a BJT only three. So if you understand the MOSFET, you understand the BJT. So I'll only cover the MOSFET. Um, I would recommend, however, to go back and watch the previous video before watching this one because Miller's theorem is very, very important. I can't stress this enough. A lot of people don't even focus on it, don't understand it, and they just move on and try to do other stuff, and then it messes them up on the final exam because it is a question on the final exam. You have to know Miller's theorem. It's a very important part of the course. So, with that being said, watch the previous video, brush up on the topics, and then come back here. Okay. Oh my God, burping. Okay, so we got these two scenarios here, the BJT and the MOSFET. And inside of the capacitors, you got a if you look at a MOSFET or a BJT, for example, you have a PNP or an NPN. At the boundary of the PN junctions inside of the PNP, you have an electric field. Same thing with the NP, the N and the P side, you have an electric field there as well. So to model these electric fields, and remember, um, electric field is related to the voltage, and what kind of device models a voltage, or I should rather say, what is an energy storage element that is a voltage device? Well, it's a capacitor. So you're going to use that capacitor to model, to kind of like talk about this capacitance and effects inside of that BJT. So to do that, you're going to look at this circuit. You have your BJT, your base, your emitter, and your collector, and you have the capacitor C mu between the base and the collector, C pi and CCS. These are values that will be given to you in an exam or in an assignment for you to plug in when you're solving your problems. And when you're looking at a MOSFET here, you have the gate, source, drain. But if you look at this very carefully, you have CGD, which is between the gate and the drain, CGS between the gate and the source, CDB between the drain and the body. Now, if you remember in electronics one, when we look at the MOSFET, when we look at its physical layout, it has a body. But in this case, you know, when you're drawing a circuit and you're drawing the transistor design, your body's pretty much grounded because there's not really a terminal that you could connect it to. Does that make sense? Like there's not really a body terminal. You can't connect a wire to the body. Does that make no sense? So you're just going to connect it to ground instead. Okay, so this is between CDB, which is between the drain and the body, and the source is between the CSB is between the source and the body as well. So these two are grounded. So we want to find the poles of this MOS cascode. All right. So we have a cascode here. Now remember, you should be pretty comfortable with the concept of cascode because it's going to keep on coming up. You have a cascode circuit here with a load resistor at the output. And then we're trying to find the pulse of this circuit. So the number one thing you want to do is when you're trying to find pulse is, as I've talked before, you want to disable DC and VN. Okay, so your input voltage is going to be disabled and your DC voltage is going to be disabled because when you're finding poles and you're doing Miller's theorem, that is, it comes from Thevenin in principle. And when you do Thevenin, all the independent sources are cut off. So you remove all of them is shut down to zero. Same thing here. Vin is an independent source, although AC, so you switch that off to ground. And DC source is an independent source, so it's going to go to ground. So we have ground and ground. And the next thing you want to do is you want to draw the intrinsic capacitors of all of your MOSFETs. Okay, so you have two MOSFETs in this case. So you're going to draw all the intrinsic capacitors. So CGD, CGD, DB, DB, GS, GS, CS, BCS, B. Same thing with this one. GD, GD, GS, GS, DB, DB, CB, C, SB, SB. I don't even know what I'm saying at this point, but you get the idea. But you have to be very careful. You have to be very careful that you are connecting them correctly. You can't connect here CGD because this is the drain and this is ground. Connected between the drain and ground is not GD, it's DB. So you have to make sure terminals are correct when you're putting in the capacitors. Now you might look at this thing and you're like, oh my god, what is going on? Why do you have so many capacitors? And you might literally give up. Don't give up. Things are gonna get simpler. All right, you can simplify a lot of things here. So the first thing that I want you to notice is try to combine stuff that are parallel, right? If you can combine stuff that are parallel, remember capacitors in parallel are just the addition of them. So if I look at this one here, I got this node and then ground, ground. So pretty much these two capacitors are in parallel. So I have them in parallel right here. Okay, so that's what I got going on. So I just combine CSB2 plus CDB1. These two are going to be added right here. Okay. Now, I want to assess for non-floating, or I should rather say like capacitors that are not connected to ground. So if you look at CGD1, it's connected on one end here and the other end here, so it's not connected to ground. So I want to take care of it. Remember, we're going to apply Miller's theorem, and we're going to split that into two capacitors that are connected to ground. So that's what we'll do. And I'm going to call this CM1A and CM1B. So, okay. And why am I calling it CM1A? Is because C MOSFET A and C MOSFET 1B. All right, it's associated with MOSFET 1, and it's the capacitor at the voltage A. All right, capacitor of the MOSFET B, number 1, MOSFET 1B, associated with the voltage B. And what is VA/VB? That's the ratio between VA and VB. AC, of course, the AC ratio between VA and VB is going to give me the gain equation that I can plug into my pole equation for me to find the pole of that circuit. Now, if you don't remember, or I'm not making sense at all, go back, watch the pole identification video. So pretty much CM1A is going to be governed by this equation through pole identification. Again, I can't stress this enough. Go watch the previous video if you want to have the equations of pole identification. But CM1A is going to be 1 minus the gain, AV1, where AV1 is going to be the difference between VB and VA. All right, the AC gain, or I should rather say the ratio, the AC ratio between VB and VA. All right, and CM1B is going to be 1 minus 1 over the gain of CGD1. There should be a C here. There we go, CGD1. So now that I have these two equations here, I'm going to go ahead. What is going on? Honestly, did I copy paste this well? Hold on. Okay. I'm just trying to make sure if everything's okay. Okay, let's go back here. So that's what I'll do. So now we want to find the R out, right? Because what the hell? M2, M1, or M2. Sure. We're gonna find the R out of this circuit. Okay. So I'm just trying to follow up because it's been a while since I've done this. So I'm just gonna look and trying to see what I did and why I did it. Okay. So if we're trying to find R out of the circuit, R out is given at the V out here, looking inside of the circuit, and you want to eliminate all of your capacitors when you're doing that. So when you're doing that, you eliminate all of your capacitors. Okay. And this M2, you can replace it, and it's not ready. That's why I got lost a little bit, because we're trying to replace this M2 by a resistor, but it's not readily available in the cheat sheet. So you have to derive it. So this is why I have this going on here, because I derived it, right? I want to replace, because I'm trying to find R out. I'm trying to find R out of this circuit, but I need to replace this circuit by an equivalent resistance. But it's not available in the cheat sheet, so we're going to use AC small signal model. So I have the gate, the source, and the drain. And here I have VGS, GM VGS, and RL. And over here, the gate is connected to ground, the drain is connected to RL, and the source is going to be connected to the Thevenin voltage that I do give into the circuit with a 1 ampere current. All right, if you don't remember how to do this, I have electronics 1 videos, you can see how to do this. Okay. So here, what I can tell that VGS is VG minus VS, where the gain, oh my God, where the gate, oh, what the hell, man. Okay, where the gate is grounded. So VG is 0. So VGS is equal to minus VS. Okay, and you can see that VT and VS is the same thing, right? VT and VS is pretty much the same thing. So if VGS is minus VS and VS is VT, so VGS is minus VT. All right, so that's one thing. And the other thing is, you can see that this current here, 1 ampere, is flowing through this wire right here. But I know that the current flowing inside of this wire is GM VGS. I do know that VGS is minus VT, so this turns into minus GM2 VT. And this has to be equal to -1. Why negative? Because I said 1 ampere going in, but I know from the current source is coming down, so I need to flip the signs so that they are equal. Okay, so GM VGS equals to -1. GM VGS is minus GM2 VT. The minus signs cancel, and I have VT equals to 1 over GM2. So when I find VT, I find RM2 because they're equal. Why are they equal? Because I have 1 ampere current going into the circuit. V equals IR. If I is 1, V equals R. So RM2 is equal to 1 over GM2. So now I have that. So the moment I have this, I can replace my RM2 by 1 over GM2. Now again, I'm going to use classic method to find my R out right here. Classic method. Okay. So how do I do this? I have M1 right here. I'm going to replace by small signal model. So the gate is connected to V1, but remember V1 is grounded because I'm trying to find R out. Okay. And then the source is connected to ground, and the drain is connected to 1 over GM2. Okay. And I'm giving 1 ampere current into the circuit because I'm trying to find R out. Let's do that. So this is gain V. The voltage of the gain is 0, the gate is 0, and the voltage of the source is 0. So VGS equal to 0. If VGS equal to 0, then the current source here is equal to 0. So your circuit simplifies to this highlighted box right here. And VT is the voltage across this resistor. So VT equals to 1 over GM2. So R out is 1 over GM2. Okay? So that's it. That's pretty much it. So your gain is going to be AV1, which is minus GM R out. Now, what is GM in this case? GM is the GM of the input resistor, which is connected to the input source by bro code. So this is your GM, and then this is your R out. So your gain is minus GM1 over GM2. Okay, and what is AV1? AV1 is pretty much the AC ratio between the point B and the point A. All right, so that's what we're trying to find, right? So all these concepts, they come together. So CM1, this capacitor is governed by this equation. CM2, CMB is this capacitor governed with this equation. AV1 and AV2 is governed by the ratio between VB and VA. And AV1, we just calculated, it is minus GM1 over GM2. So I can take this gain and I plug it into this equation. And then I have my equations for CM1A and CM1B. Okay, so that means, what does that mean? That means I can ignore this capacitor because I have this in terms of stuff that I know. So then I have 2 more capacitors that are connected to ground, and that's very good news for me. So here, my circuit becomes as such. All right, if you look at the situation here, you will see that we have even more stuff that can combine. All right, so if you look over here, this is VA for both, and both of them are connected to ground, so you can combine these two. By combine, you add this too, and you have only 1 capacitor right here. You can add them. All right, previously we had added this one, but this is VB, and all of this is VB. This is ground, so this is parallel. So you're going to add those together. You're going to combine those two together. And actually, if you pay close attention, this is still VB and this is ground. So all of these are in parallel. All of these are in parallel. Okay. As well. So we have all of these in parallel, these in parallel. And then if you look closely over here, V out, this is V out. Okay. And then this is ground and this is ground. So these two as well are in parallel. Okay. These two are as well in parallel. So now that means you have pretty much only three capacitors. You got one here, the second one here, and the third one here. Three capacitors. So you're going to have three pole equations if they're associated with a resistor. All right, remember from pole identification technique, if you have a capacitor in parallel with a resistor, that's going to give rise to a pole. Okay, so let's look at the output first. At the output, we have this capacitor in parallel with this capacitor. So we have the addition of these two capacitors, and they're parallel with RL. So my gain equation is going to be 1 over RL times CdB2 plus CGD2. All right, so that's my omega at the output. That's my pole at the output. Okay. Now we have this capacitor that we drew. All right, we combine. It's four of them. It's CSB2, CDB1, CM1B, and CGS2. That's four capacitors. But it's parallel to what? All right, I want you to think about that for a minute. What is this capacitor parallel to? Think about it. Pause the video. Think about it. Don't go ahead and then watch it. Think critically about it, and then I'll come back to it. Okay. But for the last part, I'm just going to look at this one. So we have this right here, CM1A plus CGS1. Over here, they're connected to the same point, and at the other part, they're connected to ground on both sides. So these two are in parallel. So your input pole is going to be 1 over RS times this capacitor. All right. And then what is CM1A? CM1A is this big fat equation we had right here. So I can replace it right here into my gain equation. So this is my omega P input. All I did here is nothing too crazy, is I had this in parallel with that. CM1A I calculated before, so I replaced it in my equation here, and this is my input pole. So now that I have my input pole and my output pole, I need to go back to this one. What is this equal to? Okay. So this is equal to, if you think about it, I'm trying to find a resistor here, a resistor value that is in parallel with this capacitance. Well, this transistor can be replaced by a resistor, and this transistor can be replaced by a resistor, and these two are going to be in parallel. So this capacitor is parallel to the parallel combination of the equivalent impedances of these two transistors. Take a minute, digest information. Very, very important. The resistors do not have to be physical. It does not have to be physical. The capacitor can be parallel with an equivalent impedance of a transistor. Let that sink in. I'm going to repeat. This capacitor is in parallel with the equivalent impedances of the two transistors in parallel. Okay, so that's what we'll do. So I want to replace M2 by its equivalent impedance, and we did that previously. It's 1 over GM2. And RM1, we want to replace it by its equivalent impedance. However, RM1 is not readily available in the cheat sheet, so we're going to have to derive it. So I'm going to draw the small signal MOSFET of the RM1. By the way, when you're deriving stuff on your own, I always ignore the resistor associated with the channel modulation. Usually we have RO right here. I ignore that. You don't have to worry about that here. It just makes your analysis much simpler. So here I have my gate. The gate is connected to RS, which is connected to ground, by the way. I think my ground got cut out here. All right, there we go. All right. So this resistor is connected to ground. The source is connected to ground. And then the gate is connected to the resistor RS. And the drain is connected to my Thevenin voltage because I'm trying to find the equivalent impedance at that point. Okay. So this is a short circuit, so there's no current going here. If there's no current going here, this ground is technically this ground. So VG equals 0. The source is grounded, which means VGS is equal to 0 because VGS is a subtraction of VG and VS. If VGS equals to 0, the current source value is 0, which means that, what does that mean? It means that this current is 0, but I know that the current coming inside is 1, So Rm1 is equal to infinity, right? Rm1 is equal to infinity. That means it's an open circuit. All right, it's an open circuit. There's no current flowing through it. 1 cannot be equal to 0. So what does that mean? It means that you have a resistor value parallel with an infinite resistance. What that only means is it's equal to R. All right, I'm not okay. 1 over 1 over R1 plus 1 over infinity. What is 1 over infinity? 0. So 1 over 1 over R1 is 1 times the reciprocal of 1 over R1, so it's just R1, okay? So a resistor parallel with an infinite resistance is just the resistance itself. So this is what I have here. Actually, I have the proof right here. There we go. So R is equal to GM2, 1 over GM2. So this is the parallel combination of these two resistors right here. This is R, and R is 1 over GM2 parallel with infinity. But this goes away, so R is 1 over GM2. So this capacitor, what is it parallel to? It's parallel to 1 over GM2. And what is 1 over GM2? 1 over GM2 is the parallel combination of the equivalent impedances of M2 and M1. So omega P is going to be equal to this equation. So this is omega P for the pole by the middle capacitance. So we have an input pole, we have an output pole, and we have this pole. Now, I want to introduce something called the transfer function. The transfer function is something. It's an equation that gives you information about the input and about the output of your system. And this, what I want you to understand, A0 is your regular circuit gain with no capacitors. So if you have a capacitor, you compute its gain is going to take the value of A0. Depending on the number of poles on your circuit, though, you're going to have this equation: 1 plus S omega over omega P1, omega P2, omega P3 until omega Pn. Pn is the number of computed poles. It's how many poles you have in your circuit. In our case, we have 3 poles, so we're going to stop at 3. In the future video, I'm going to explain how to fill up this transfer function for you to be able to find the transfer function of your circuit when you do solving problems in this course. What I want you to keep in mind is S is equal to j omega. All right, that's a Laplace variable is S is equal to A plus j omega, or I should rather say S equal to sigma plus j omega. The guys taking signals and systems, you guys would see that. And when sigma goes to 0, S equals to j omega. So that's your Laplace transform variable when sigma goes to 0. So that's pretty much the concept behind it. And I will show you how to fill up this transfer function in the next video. But you have to understand all the workings of this video and the Miller's theorem video for you to move forward into transfer functions. With that being said, I hope you guys enjoyed this one. This one was a mouthful. This is where the class really starts to pick up. It's not an easy course per se. You have to be very apt with all of the things, electronics, electronics 1 methods, electronics 2 methods, and your circuit solving problem with all that stuff. So I think it's time for me to check out and go to bed.